Welcome, everyone. My name is Olivia Roth. I'm the Associate Director of Student Affairs for Penn Engineering Online Learning. This is a MCIT Online admissions webinar. And today we have a guest speaker who's going to talk to us on a specialized topic that we thought you might be interested in. So you'll be welcome to ask questions about blockchain. And then at the end, we'll also have time for some general questions, admissions questions if you have those as well. So let me just pull up our presentation here, and then introduce our celebrity guest. Here we go. Okay.
Hi, so I'm Brett, and I'm faculty in the computer science department, and my research focuses on cryptography. And recently, I've also been looking at some of the cryptographic aspects of blockchain. And so I want to give a quick overview of some of the blockchain technology and end with some of the cool research questions that are coming up in this space. So I think when most people hear blockchain, they think of cryptocurrencies. And looking this morning, Bitcoin has a $233 billion market cap with Ethereum trailing and Ripple in third place. And even this is changing a lot. I made these slides yesterday and I had to update them this morning because Bitcoin's market cap jumped $10 billion. But the impetus for building these cryptocurrencies was really to try to decentralize the banking industry. So the traditional way you transfer money is you have money in a bank, and if you want to send money, you ask your bank to initiate a transfer for you. And the central authority, this bank is a central authority that controls all of your transactions. And so that gives them a lot of power to censor transactions or to freeze accounts or to charge high fees. And so the goal behind Bitcoin and most of the subsequent cryptocurrencies was to sort of decentralize this role of the bank, to try to take some of this power away from the bank, where transactions are still submitted by users, but instead of being authorized by the bank, they're authorized and executed by a decentralized network of servers. And this was mostly to fight this kind of censorship. So here are some news articles. If you go to Google News and you look around, you kind of find these things all the time that, you know, my accounts have been frozen because I was wrongly suspected of being a terrorist, or because I sent money to someone in a country that is not on friendly terms with our country. And so this is the kind of thing that most of the cryptocurrencies were designed to combat. And so the main benefit that they would give you is this kind of decentralized control. There's no central authority that can halt transactions or reverse transactions or freeze accounts. One of the flip sides of this is that means you as a user don't get any of the fraud protection that you would get with a traditional bank, right? When you have a credit card and you see some charges that aren't your own, you call up your bank and you say, these weren't mine, and most of the time they'll refund that money to you. Right, there's no central authority in these cryptocurrencies that can kind of do that, and that's led to a lot of problems actually, right? That once a transaction happens, it's happened, and there's nobody to call to get your money back. And so lots of money has been lost in this way. And this is sort of a trade-off that you get by eliminating the power of this central authority. So I want to talk a little bit though about sort of the blockchain design. And the reason I want to go into some of this background was to say what motivated these designs in the first place. Because a lot of people think about blockchains as being a system for private transactions, but they're not really about privacy. They're really about decentralized control. So blockchain in general is basically just a way for a group of people to agree on the state of a system. And in cryptocurrencies, the state of the system is the state of everyone's account, their account balances. And so the state of a system is it's just a sequence of updates to the state, in which case an update is a transaction. So when I send money to somebody else, that updates the system. It updates my account balance and the receiver's account balance. And blockchains really actually don't use that much cryptography. They tend to use a hash function, which is going to help determine the order of the updates, and cryptographic signatures, which allow you to verify who requested a transaction, so that only I can remove money from my own account. So we'll talk a little bit about this. And these two things is really enough for cryptocurrencies. If you can order all of the transactions, that can prevent all of the double spending that you're worried about, right? So if somebody has $10 in their account and they try to send, $5 to one person and $7 to another person, well, one of those transactions is going to bounce, and the one that bounces is the one that happens second. So as long as we agree on which one happens second, we can basically say the second transaction is invalid because it would have overdrawn your account. And the signatures are just to say that only the account owner can withdraw money. And so on these blockchains, most of them use a hash function, which in many cases is the SHA-256, which stands for the secure hash function. And the hash function basically is a deterministic way to map arbitrary strings to a 256-bit fingerprint. And so it's a way to get a short digest or a fingerprint of any piece of information. And the security property that you want here is that it should be computationally intractable to find collisions. So to find two different things that have the same output. So two different inputs that have the same output. So that would be like, finding two people with the same fingerprint. And now, just from a counting argument, that there have to be collisions. If a hash function can take arbitrary length inputs, it can take anything as an input, it can take an image as an input or any bit string, and it outputs always a 256-bit string. That means there are only 2 to the 256 possible outputs, but there are more than that many possible inputs, so there are collisions. But the guarantee is that it should be hard to find them, that basically the best way to find them is a brute force method where you just sort of try inputs until you find 2 that collide. And with SHA-256, no one has actually found a collision yet. And the other cryptographic component that these systems use is a digital signature scheme. And most of them use an ECDSA, which is an elliptic curve digital signature algorithm. And these are actually a fundamentally different kind of cryptography than hash functions. They're what's called public key cryptography. And here there's a signature scheme will have a pair of keys that are generated together, a public verification key and a private signing key. And anyone can generate this pair of keys, and then this pair is tied together. And with the signing key, you can sign a message, and then anyone who has the corresponding verification key can verify your signature. So anyone with a public verification key can verify that a signature came from that specific signing key. And so this solves a lot of the problems if functions like a signature in real life. But one of the challenges that still remains, and that's actually very hard to address both in cryptocurrencies and outside, is how do you know you have the right verification key? So you see a verification key and you think it belongs to me, and then you can verify signatures that, that came from the signing key associated with this verification key. But if you're incorrect about who created that verification key, right, you will also be incorrect about who signed the message. And so this is actually a real challenge. And so with these building blocks, a blockchain is actually exactly what it sounds like. It's a chain of blocks. And these blocks tend to be structured in this way here. It's like this diagram where they have a payload, which is like a bunch of transactions, and they have a hash value, they have a fingerprint. And that hash value is a hash function like SHA-256 applied to the previous block in the chain. So each block says, here are the bunch of updates I'd like to make. So here are a bunch of transactions I'd like to process, and here is the fingerprint of the preceding block. So each block tells you what the previous link in the chain was. And the hash function, because it's collision resistant, means that you can't later insert a different block into the middle of the chain. So you can always insert blocks on the end. So this is basically what becomes an append-only ledger, because you can always add a block at the end and you can always calculate the hash of your predecessor. But if you wanted to insert something in the middle, then that would break this chain of hashes. And so the nice thing about this type of structure is that if we can agree on the first block, which is usually called the genesis block, and usually it will be like an empty string that we agree on. And if we can agree on the last block in the chain, which is the last block, then the string of hashes means that we can agree on the entire block of the entire chain. And if we agree on the entire chain, then we agree on the entire sequence of updates or the sequence of transactions. And so then we also have to agree on everyone's account balance and the complete state of the system. So the nice thing about this structure is basically it means that if we can agree on just the last block, what was the latest thing that happens, then we know we're in sync together. And here's a quick diagram of basically why hashing makes this chain append only. So if you try to insert this red block of transactions in between two existing blocks, basically the hash on the block on the right will no longer match. It's supposed to have the hash of its preceding block, and it won't match the hash of this red block. And there's no way to create a hash. The hash of the red block will always be different from the hash of the block on the left because of this collision resistance property of the hash function. And so you can basically, the hash functions mean that you could always detect if somebody had tried to insert a block into the chain. And so this means that once the blocks are created, their ordering is fixed. And so in particular, the sequence of all the updates and the sequence of all the transactions, their order is fixed forever. And all you can do is sort of append on the end. So what this means basically is in order to agree on the state of everyone's account balance or the state of the system, we just have to agree on the last block. So how do we do that? And it turns out that in a distributed setting, agreement is actually really hard. So here's the sort of simplest example. Suppose you have three people, Alice, Bob, and Charlie, and they want to agree, and they all have some idea of yes or no. And Bob thinks yes, and Charlie thinks no. But if they can't all talk to each other at once, they can just talk to each other in a peer-to-peer and point-to-point channels. Then Alice can basically trick Bob and Charlie. If Alice tells Bob, I'm voting yes, and she tells Charlie, I'm voting no, then Bob sees two yes votes, his own analysis, and Charlie sees two no votes. And Bob thinks the majority is yes, 2/3 of them voted yes, and Charlie thinks the majority of them voted no, right? And so both Bob and Charlie saw a majority go in different directions, right? And so they did not reach some agreement of what the majority vote was. The system is split. And so this is exactly the consensus problem. And so the initial formulation of this problem by computer scientists use this terminology of Byzantine agreement, where there is a story that you have a number of generals who are deciding whether or not to attack a fortress. And they have to decide on the same plan of action. And if enough of them choose to attack, they will succeed and take the fortress. And if only some of them attack, they will have insufficient force to take the fortress, and they'll be crushed. And so the question is, can you design a system where the generals can either all agree to attack or agree to stay back and hold their forces for another day in a way that a small number of traitorous generals can't cause the honest generals to adopt a bad plan of action? And there were solutions in computer science from the early 80s, and these classical solutions, though, require you to know sort of in advance how many people are participating, how many generals you have, how many people are agreeing, how many people you're running this consensus protocol for. And so they don't work very well if you don't know all of the people who are going to be involved in this decision, or the number of people that involved in the decision could vary. And so that's where some of the new ideas that came out of Bitcoin came from. So Bitcoin, for its consensus mechanism, uses a proof of work, which instead of being a sort of one person, one vote scheme is often referred to as a one CPU, one vote. And basically it's implemented in a way where it's your chance of being able to create a new block. So who's going to append a block to the ledger? This is done in a sort of lottery fashion, and anyone can participate in this lottery. And the way you participate is you try to solve these little crypto puzzles, these proofs of work. And your chance of winning the lottery, of being elected the leader to create the next block, is proportional to how much computing power you have. So these people who want to be a validator, they compete to solve a little crypto puzzle. And these crypto puzzles are designed to be very hard to solve, but easy to verify. So if I solve it first, I can tell everybody, look, I solved it, and everybody can verify quickly that I solved it. And if I solve it, then I'm given the sort of right to create the next block. I'm given the authority to put the next block of transactions on the chain. And this is really nice because now we don't have to know in advance sort of how many people are going to participate in this consensus, how many people want to be validators in the Bitcoin system. Validators can come and go. But the big drawback of this kind of system is that it's very wasteful from a sort of time and energy perspective. You have all of these potential validators who are working to solve these crypto puzzles, which are mostly useless, and they've invested millions of dollars in hardware to do this. And currently, Bitcoin validators use about as much electricity as Switzerland in order to validate Bitcoin transactions. But right now, Bitcoin and Ethereum and many of the popular cryptocurrencies do use a proof of work system like this. And most of these proofs of work are structured in a way, they're just solving these hash puzzles. It's saying, can you find a random value R such that when you hash that random value R along with the last block in the blockchain, that it has a bunch of zeros at the beginning or at the end. So if you remember like SHA-256, the output is 256 bits. And so can you find some input to the SHA hash function where the first 32 bits are 0? And essentially the way to do that is you try a lot of inputs and you see what happens. And you just try them as fast as you can. In order to improve efficiency, a lot of systems are thinking about a kind of proof of stake model, which is now, instead of, again, a one person, one vote, or one CPU, one vote, it's kind of a $1, one vote. And so these systems are all usually also designed as a lottery. And at every block, there's a lottery of who will have the right to produce the next block. But here, your chance of winning the lottery is proportional to the number of tokens you have in the system already. And the argument for something like this is that people who have a lot of tokens in the system have a lot invested in the system already, and they are the people who have the most sort of skin in the game and have the most incentive to make sure that the overall system stays stable and intact. And so in order to attack this system, you would need to invest a lot in its underlying cryptocurrency or its underlying token in order to gain any significant chance of sort of winning this lottery. And so that's kind of the argument for systems like this. And the nice property of a system like a proof of stake system is that you don't need to waste a lot of time solving crypto puzzles. And there are a number of blockchains that use this kind of system, like Cardano and Algorand, and Ethereum 2.0 is planning to move to a proof of stake system as well. But these systems are challenging to design, and they're from a cryptographic perspective, and they're challenging to analyze from an economic perspective. And so we're only just sort of scratching the surface still on the best way to design proof of stake systems. A third type of consensus model is a permissioned consensus model. And this is much more similar to these classical consensus models where it really is sort of one person, one vote, or one entity, one vote. And these systems only work in a place where you know all of the potential validators. And so these work in a lot of these closed business environments. If you have a bunch of banks that are going to try to run some kind of consensus algorithm, they know in advance how many people are participating. No one is creating sort of, fake accounts to flood the system with votes. And these systems can be very fast, but they don't address a lot of the sort of openness goals of the original cryptocurrencies. But systems like Hyperledger Fabric, R3 Corda, and even Facebook Libra are built in this permissioned model. And so they have a fixed set of validators who are running. And now one of the things that I want to talk about, because it's sort of closest to some of my research and some of the most interesting questions here about privacy on the blockchain. So blockchains give a good way for a lot of a distributed system to agree on the state of the system, but they don't inherently provide really any kind of privacy at all. And actually on Bitcoin, right, every transaction is public, and the same is true with Ethereum and with Ripple and most of the popular cryptocurrencies. And this was recognized even at the inception, the Satoshi Nakamoto's first paper that introduced Bitcoin cryptocurrency. He pointed out that actually Bitcoin will have in some ways less privacy than a traditional banking system, because in a traditional banking system, maybe your bank knows all of your transactions, but they don't share that with everyone else. But if you want to have a distributed group of people validating all transactions, it's hard for them to validate a transaction without seeing that transaction. And so the transactions sort of inherently have to be public. And so this is a big challenge, right? It's sort of how can you get this public verifiability, but also have some kind of privacy? How do you prevent double spends without revealing what the transactions are? And the Bitcoin solution was not to really provide privacy, but to provide what's called pseudonymity. They said, well, all the transactions will be public, but they don't have to be tied to you. You can always create new accounts, and these accounts will be your pseudonyms. And so you can create as many accounts as you want. And in fact, we recommend that for every new transaction, you create a new account, and that will make it sort of harder to link what you're doing back to any real world persona of you. So even though the transactions are public, they're not tied to any individual, and each individual may have a lot of accounts. But actually, it turns out that this did not provide much privacy, and there's this series of academic works that showed that you can de-anonymize a large fraction of Bitcoin transactions just from transaction patterns. And if you start linking these transactions to other sources of information like people's IP addresses or cookies that other websites have put in on their browsers, you can actually start linking a lot more. And so this means that you'd really need a change in design to get any kind of privacy in these systems. And so there have been a few privacy preserving cryptocurrencies, and Zcash and Monero are two of the biggest of these. And Zcash uses a cryptographic tool called non-interactive zero-knowledge proofs, which allows the participants in a system to essentially prove that their transaction is valid without revealing anything about the transaction itself. And Monero uses a different system of ring signatures and stealth addresses to sort of anonymize senders and receivers. And so these systems had privacy goals in mind to go beyond the privacy of Bitcoin. But actually, in their initial designs, they did not live up, I think, to their privacy goals. And part of this was actually just about usability, that these systems, Monero and Zcash, both had defaults that were not particularly private. So if you went in and you started using these systems and you used the default settings, you actually did not have as much privacy as you thought. So for example, in Zcash, in order to be sort of backwards compatible, it supported transparent transactions and shielded transactions. And shielded transactions provide a lot of privacy, but it turns out most people didn't use them. And actually in a recent paper, they said almost 3/4 of the transactions are transparent, which means that they're essentially, they give you the same privacy that Bitcoin would have given you. And so to address this, like Zcash is upgrading their protocol to make privacy the default now. And so I'm looking forward to seeing sort of how the privacy preserving features improve as these systems develop. And so blockchains, they'll also have a lot of applications beyond just cryptocurrencies. So I'm going to talk about a couple of these really quickly because they also present some really interesting privacy challenges. So if we recall, a blockchain is really just a chain of blocks, and essentially it's just a method for a group of people to agree on the order of transactions. Or another way to say it, it's a decentralized append-only database. So where can you apply such a thing? Where do you want a decentralized append-only database? And so some of the places that this has been proposed is in supply chains. So people may want to know, they want to be able to track the location of their physical goods, either for end users or for the participants in the supply chain. Another application is land registries. You want everyone to agree on who owns which piece of land, right? This is actually a challenge now. If you've tried to buy a house, you may have been encouraged to buy title insurance, and title insurance is an insurance to say, even though you bought this piece of land, maybe the person who sold it to you didn't actually own it, right? And that's because record keeping is really not that good. We can't agree on who owns every piece of land. An application that I really like for blockchains is this identity management. How can we all agree on credentials that someone might have? So how can we agree that you got your degree from some school, for example, or that you were employed by a specific employer. So let's talk a little bit about this supply chain application for a second, because there have been a lot of pilots in this space. And there are actually a lot of different goals for supply chain. There are goals for end users. So a lot of end users may want to know that their products were ethically sourced. They want to know that their meat was ethically sourced. They want to know that their clothing was produced without child labor. They want to know that the diamonds they buy weren't blood diamonds. And so the only way to do that is to be able to sort of prove to them in some way that the sourcing of their materials and the manufacture of the products was actually in line with their sort of ethical goals. The retailers and the people inside the supply chain actually have different goals, and mostly they would like to optimize logistics. They'd like to know, if a shipment is delayed, was it hung up on customs? Was it just left on a loading dock somewhere? Did the shipper take too long? Was the was the manufacturer just slow in producing it? And if you could get this information in an efficient way, you could optimize logistics, and you could prevent loss, and you could prevent theft along the supply chain. And so one question is, well, you'd like to have a database for this, but why does it need to be decentralized? We've had databases for decades. Why a decentralized database? Why would you want the overhead of something like a blockchain? And one of the big arguments is that basically, if you had a centralized database, whoever owned that database would have too much power. And this is sort of the same argument that came up in the banking industry, that if you have one bank that maintains everyone's account balances, or if you have one company in a supply chain that maintained the records of everything else that was going on, that would give them sort of too much power. And so who would own it, right? All of these companies that are working together, but somewhat in competition, right, would scramble to sort of claim ownership of this. But if the database itself is decentralized, no one can own it, and so no one can prevent other people from accessing it, and no one can change the data in their favor. And this means that you can have a database that everyone can use and can provide value to the system without companies having to sort of cede power to their competitors. But there are a lot of privacy issues that now come up, because if you have a decentralized database and all of the database updates are public, now how do you ensure the privacy that you need? And so for end user applications, you may not need to put that much on a blockchain. So if you want to know that, say, your diamonds were ethically sourced, you may not need to know exactly how long the shipper had it in custody or something like this. But the retailers who want to use this to optimize logistics actually want a lot of information on that blockchain. And a lot of that is commercially sensitive information. And so it's a real design challenge to figure out how to manage these transparency, these auditability and privacy goals. And so a lot of these supply chain applications have been built on these permissioned platforms like Hyperledger Fabric or R3 Corda or JP Morgan's Quorum. And these have right now sort of coarse-grained privacy built in, that either you can see an update or you can't see an update. So it's not that every update is public to everyone, but they're sort of partitioned in some way, so you can see the updates that pertain to you. But this is still a very coarse-grained mode of privacy. So some of the blockchain pilots have happened. There have been some to track food products, where you buy some piece of meat here and it's got a little QR code on the back, and you scan that code and it shows you the cow it came from, and it shows you the processing plant that processed it. Similarly, Walmart had some pilots to track mangoes and to track pork. And one of the interesting things about this is that maybe you could also use this to allow people to identify disease outbreaks, if you could figure out the source of all of these different food products. A company, Everledger, was making these diamond time-lapse reports. So you could look up on when you bought a diamond, all this information about who chose the diamond and who cut it and who certified it. And again, though, this already starts to make a lot of questions about privacy, right? So say you have a diamond time-lapse report and you put on a blockchain who crafted each diamond. Well, then you could scrape that blockchain and look up for each producer, how many diamonds they crafted, or for each certifier, what certifications they gave, right? And this the people involved may not want this information public, right? If I'm processing diamonds, I may not want everyone to know how many diamonds I'm processing per year or per month, right? And then another question is, how long do you continue to track these diamonds? If you want to track ownership to make sure that these diamonds weren't stolen, then maybe when someone buys it, that's also recorded on the blockchain. But as an end user, I may not want my purchase recorded on a blockchain where other people can look it up, because maybe I don't want my neighbors to know that my basement is full of diamonds, right? And already this is just a tiny amount of information. This is not the amount of information that you need to do actually business analytics. This is just the information you'd need to be able to maybe say that a diamond was not a blood diamond. But if you wanted to include stuff that would be useful for optimizing logistics, you'd actually have to have a lot more things about how long it was on each truck and who signed for it. And that would give you a lot of information about the intermediate shipping companies that they may view as commercially sensitive. And so the participants in these systems know that privacy is a challenge, and they've said, look, we want to build a system that's both transparent and is auditable, but also provides the necessary kind of privacy. But they still don't know how to do it, and everyone is still looking around for the best way to sort of manage these expectations between auditability and privacy. And this is actually one of the areas that I think is one of the most interesting areas of research now. And so in a lot of these systems, right, there is this trade-off between transparency and privacy. And addressing these questions, actually, there's some technical sides of these questions about what types of cryptography to use, but there are actually a lot of domain-specific questions about what kind of privacy do the actual participants want, or what kind of privacy do they need, and what data needs to be shared and what data can be hidden from people in order to do a kind of audit. And these are questions that you can't just answer in isolation. You can't just answer sort of mathematically. You have to actually get down and talk to the people who are involved in this specific use case. But there are a lot of tools from cryptography that can help. And so two of the tools that I am most excited about are these zero-knowledge proofs, where you can prove to someone that you did something correctly, or that you had some information without revealing what it is. And so this is the type of thing that Zcash is using, that I can prove that if I make a transaction, I can make an encrypted transaction, and my account balance is, say, encrypted, and I can prove that the transaction I'm requesting will not overdraw my account balance without revealing to you what the transaction was or what my account balance is. And so that gives you a lot of power to have both privacy and auditability. And another area that I'm excited about is the secure multi-party computation, where it basically is a general purpose tool for allowing people to compute aggregate statistics on private data. And this is an area that I work in heavily, and it gives you a lot of power to cooperate and collaborate in a privacy-preserving fashion. And now merging these tools like zero-knowledge proofs and secure multi-party computation with blockchains opens up a whole new avenue of cryptographic applications. One thing I just wanted to mention at the end, another major engineering challenge in all of these blockchain systems is scalability. That these systems, once you have a distributed database, in a lot of distributed systems, if everyone is talking to everybody else, then the amount of communication essentially grows quadratically with the number of people involved. And that doesn't lead to something that's scalable. And so a big challenge in all these systems that's separate from the privacy challenge is, how can you make these systems scalable, that they can process enough transactions? And this is still a very active area of research. So that's my brief overview on blockchains for today.
Awesome. Thank you. So we got a couple of questions that came in while you were talking, and people were able to vote on them. So
okay.
I'll read off some of them now, but I did wanted to mention that if you are joining us by phone, unfortunately we don't have a way for you to submit questions in real time. But if you think of a question later, you can send us an email at online-learning@seas.upenn.edu. And we're also recording this webinar so that you can reference it later if you would like. So the first question is, will the invention of a quantum computer jeopardize the security of blockchain?
Okay, yeah, so this is a great question. And so some people may have heard that if you could build a quantum computer of a reasonable size, that would break a lot of the modern public key cryptography. And so right now, people have managed to build small quantum computers, but nothing of a scale that could jeopardize the existing cryptographic implementations. But there's a distinction about what you could break with a quantum computer. A quantum computer doesn't just break everything. So actually, right now, functions like the SHA, the secure hash function, are not susceptible to quantum attacks that we know of. So the hash functions that we use today, we believe are quantum resistant and wouldn't have to change at all if a large-scale quantum computer were invented tomorrow. What would have to change is a lot of the public key cryptography. And so in particular, these Bitcoin system or blockchain systems that are in place today use digital signatures. And the digital signatures they use are mostly based on elliptic curve cryptography. And most of the elliptic curve cryptography we use would be vulnerable to a quantum attack. And so those existing signatures would be vulnerable. And so if you had a quantum computer that you didn't tell anybody about, you could forge any kind of signature you wanted, and you could empty all of the accounts on Bitcoin tomorrow if you had such a computer. Now, from an engineering perspective, that's not a huge problem because we have a lot of alternative signature schemes that we believe are quantum resistant. So if you saw that a quantum computer was coming, you could swap out the elliptic curve signature schemes that we're using for quantum resistant signature schemes. But that would take a sort of long time because you'd have to rewrite a lot of this code. So the answer is that quantum computers will change things, but it won't be, I think, a death knell for most of this cryptography. We have alternative quantum resistant things, and the reason they're not ruled out now is that they're just a little bit slower than the existing non-quantum secure systems.
Okay. Another one is, who is the control authority over these hashes? Or does the decentralized nature prevent control of some kind? And then if so, how are the hashes originated then?
Okay, so there's a lot of interesting questions about control in the blockchain system. The hashes themselves, so the hash function that people use in order for it to be useful, so the point of a hash function is to be able to create a short fingerprint of any file or any bit string or any piece of information. And so in order for that fingerprint to be useful, we want to be able to make sure that if I apply a hash function to some file and you apply the hash function to the same file, that we would get the same fingerprint. And that's actually how hashes were used most of the time before blockchains came out, right? Hashes have been around for a long time, and you actually use them all the time on the internet. And that basically, if you try to download a large file, and you want to know, how do I know that when I downloaded it that I got the same thing that I was supposed to? I download, a few gigabytes of information. How do I know that I got the same file that the server tried to send me? Well, one thing is the server can compute the hash, and then I can compute the hash of the file when I get it, and then we can compare these two short 256-bit strings, and I don't have to re-download to make sure that I got it all right. And if the hash is matched, then we can be guaranteed that I got the same thing that the server sent. And so in order for that type of system to be useful, we need to make sure that we are using the same hash function. There are hundreds of hash functions that have been proposed by cryptographers, and if we use different ones, we'll get different fingerprints. And so in order to make sure everybody's on the same page about this, NIST, the National Institute for Standards and Technology, actually has had competitions to standardize hash functions. And so they've had 3 of these now, and SHA-2 is what's mostly being used in a lot of these blockchain systems. And that was standardized by NIST in the early 2000s. And they've actually come up with a new standard, SHA-3. And so part of NIST's role is to ensure that everyone agrees on the hash function. And since the hash itself is deterministic, and you agree on what the function is, then we agree that basically the output of any given hash applied to something will always be the same. Now, a question, there's a sort of a level back that's not exactly about the hashes, but who controls the actual blockchain system. And that's, there's a lot of subtleties there. So one question is, right, how do we agree? We all say are going to agree on like the last block of a blockchain, and that last block has a hash of the preceding block, and that has a hash of the preceding block, and so that tells us sort of what would allow us to agree on all of the preceding blocks. But how do we agree on this last block? And that's where these different consensus algorithms come into play. So something like proof of work says we're going to have this kind of proof of work lottery where you get to build, whoever sort of, solves this crypto puzzle first gets the right to add a last block to the chain. But anybody could create these chains, and so we have to now say, well, which chain is sort of the valid one? And so there's a heuristic for Bitcoin, which is that the longest chain is the valid one. Because you have to solve a proof of work in order to append to the chain, we say that the longest chain is the one that's the true chain because the most work went into that. And so that would be the hardest to subvert in some ways. But then there's even questions about how do we agree on what is the Bitcoin software that we're running. All of the Bitcoin validators have to run software, and they have to send messages that are in some sort of format, and they have to agree on how to aggregate transactions and which signatures to accept and which hash functions they're using. And that is actually a challenge. That's handled by a loose consensus of people. That's not a cryptographic consensus. That's people yelling at each other on Reddit and saying we should make this kind of software upgrade. Yeah, so.
Yeah, I see what you mean. There's a lot.
I don't know if that answered the question exactly, but there's lots of layers of agreement that needs to happen for a system like this.
Yeah. Okay, let me do 2 more blockchain questions, and then we'll do a few emissions questions. So I liked this one. What books do you recommend for learning about blockchain technology? I'm a good way through programming the open blockchain. I was looking for more material.
Okay. So yeah, there are a number of good books that have come out recently. Mostly, I'm coming at this from a different side of things, but I've been working in cryptography for a long time, and so I've approach blockchain from reading the academic papers that are coming out in the crypto world. So I don't know if I have actually, unfortunately, I may not be the best person to ask for the for this, unfortunately.
Well, maybe maybe even just like current articles.
Yeah. So the articles are coming out so fast. One thing is Kevin Werbach's book is an excellent book. Kevin Werbach is at Wharton here on blockchain and trust that gets at a lot of these issues around blockchain systems that they require. They are trying to supplant some sort of trust in a centralized authority, but they require still their own kinds of trust. And it gets at a lot of these really important questions that I think people have overlooked a little bit. Yeah.
Cool. Yeah, it seems like there's a lot of ethics kind of woven into this whole topic.
Yeah, one of the things that's so interesting about blockchain is that there's so many different fields coming together, that there's engineering, and there's regulation, and there's law, and there's economics. And a lot of people are still approaching them from one domain or another, and it's leading to systems that don't sort of behave the way you expect, because if you want to make a currency, there's a lot of regulatory and legal issues that you have to think about. And if you want to design incentive mechanisms for miners to want to mine, there are a lot of sort of, economic game theory kind of models that you have to think about. And if you want to design the cryptography, there's a lot of engineering questions. And if you want to have a scalable system, right, there's also a lot of engineering questions. And if you address from one side or the other, you end up with solutions that sort of don't match real world problems.
Mm-hmm. Interdisciplinary is the way things are going. That kind of leads to another question about the proof of stake system.
Yep.
I was wondering this as well. Does it favor the rich or those?
So this is a big question, right? So a lot of the cryptocurrencies were designed with a sort of libertarian ethos in mind. And so having a system where you say that your chance of becoming a validator or becoming a leader for a next round is proportional to your stake in the system. Does this lead to a world where the sort of rich get richer, right? Will this give you a consolidation of tokens, which will then lead to the same kind of consolidation of power that you were trying to avoid in the first place? And the answer is that people don't really know. This is one of the things I was getting at, is that you'd want, if you were designing a proof of stake system, you'd really want some good analyses and some good economic models about what's going to happen and how people are going to behave. And then you'd like to look empirically, do these systems function the way you think they should? And these kinds of things, what will happen, what's the stable state of these systems, depend a lot on low-level choices about how you implement proof of stake. So proof of stake is sort of a catch-all term for all kinds of different systems. They're very, very different proof of stake systems, and they have different kinds of properties, and most of them have not been really well analyzed from an economic perspective to say, will you have some sort of accretion of tokens among the rich? And so we're starting to see just some of these analyses now, but it's such a new area that people really don't know that question, but that's definitely a valid concern.
Mm-hmm. I have a question, which is that in the MCIT degree program, there are 6 core courses that kind of bring people up to speed, and then people can take electives after that. So in the 6 core courses, there's different topics that are covered, like there's math courses, there's algorithm courses, there's introduction to software development. So how do those courses kind of prepare you for working with blockchain?
So I think the blockchain course that we're preparing now, I think, will not have too many electives because it will
prerequisites.
Prerequisites in terms of, but it will be the cryptographic aspects. I think will try to be mostly self-contained because there's actually, as I was mentioning here, a lot of the crypto that's being used in these blockchains is actually fairly simple crypto, and what's interesting is the ways in it's being put together. But I think the programming courses and the algorithms courses will definitely help understand sort of how these systems are built. So the algorithms courses tend to focus a little bit more on the theory behind things, and so if you want to analyze questions about how will a consensus algorithm fare as the number of people scales up, that's going to be really important. A lot of the programming courses, right, with the blockchain systems, one of the things that's so nice about them is that almost all of the software is open source, and so you can sort of jump right in and start playing with them. And you can download and install a Bitcoin validator, and you can start scraping Bitcoin transactions, and you can start writing smart contracts in Ethereum. And so if you have some basic familiarity with programming, you actually don't need much more than that to start sort of interacting with these blockchain systems. They're much more open than a lot of the existing sort of financial infrastructure. If you wanted to figure out a way that you could accept payments from a bank, that might be kind of hard, but creating a little wallet where you can accept Bitcoin payments is actually really easy. And so I think that's just having some basic programming familiarity, you can immediately start diving in. And if you have questions about like, oh, how many transactions were happening, or what's the correlation between, Bitcoin prices and Ethereum prices, or, right, you can actually, all those data are available. And if you have a little comfortability with scripting, you can start gathering data and start playing systems.
Cool. That's great. So yes, I'm going to address a couple of admissions questions quickly because that's partly why we're here today. One of the questions is someone says they're worried about MCIT not being a traditional CIS degree, that would it be more difficult for people with an IT degree to break into CS careers? And I'm really glad that you asked this because this program, this degree has been on campus for about 18 years, and it's not an IT degree. So it's a Master of Computer and Information Technology, right? It's a different acronym than like a Master of Science in Engineering. But the only reason it's different is because it is for people without a CS background. So if you think about a traditional computer science master's degree, it's about 4 core courses and then a bunch of electives. Whereas in the MCIT Online degree, it's 6 core courses and electives after that. So in those 6 core courses, they're very packed with information, and there's a lot that you learn in that amount of time. And it's sort of, and that makes sense, right? Because if you don't have a CS background, it's bringing you up to speed. But when you graduate with this degree, Masters of Computer and Information Technology, your abilities and your skills and your knowledge is equivalent to that of someone with a Master of Computer Science. So even though you might not recognize the acronym, employers around the world recognize it because, like I said, it's been established at Penn and it has a good reputation. So we have on-campus alumni who have gone on to work at very high-profile jobs, and they get the same type of jobs that an MSc graduate would have. So it's really not an IT degree in the sense that, it's not something like a coding boot camp. It's not teaching you how to do tech support or anything like that. It's really it teaches you the fundamental underlying theory of computer science, so that if you were to do a boot camp, you might learn one programming language, but as we know, technology changes very swiftly and that language might go out of favor. So when you have this degree and this knowledge, alumni tell me that they can be approached with any language, and they understand the fundamentals to the point where they can teach themselves any language that might come about. So I hope that answers your question. There's another question. So we in the computer science department put out a course on Coursera that's called Computational Thinking for Problem Solving. And if you don't know about it, I would recommend it because it's created by one of the program directors, and it is a nice way to kind of try out some introductory material that will help you gauge whether this program is a good fit for you or not. It's definitely very tame compared to the rigor of the degree program, but at least it can give you a sense of some of the video production quality that we use and some of the types of assessments that we use in the degree program. So if you've taken that course or if you're currently taking it, I definitely suggest mentioning it in your application, like in your personal statement or in your resume, because it shows that you are being proactive, that you're interested in the topic. It shows that you have some online learning experience on Coursera, which is the same platform that the degree program is housed on. And so I can't give a percentage of how much it increases your chances of getting in, but I think that it's definitely favorable. We don't publish our admissions rate, but we admitted about 200 students in the spring for our first cohort and about 100 in the summer for our second cohort. So I imagine that those numbers, similar numbers, will hold steady moving forward. And it's definitely a competitive program, and we get a lot of really wonderful applications and equally wonderful students that we admit. So let me see if there's any other admissions questions. Maybe we could end with one more razzle-dazzle blockchain question. What if people, okay, this is your last question.
Okay.
What if people cheat and link unethical behaviors with ethical hash?
Okay, so I actually, I don't know exactly what that question is referring to, but the blockchain systems basically have some implicit rules about what's acceptable or what's not. So that a hash function will tell you essentially what is the preceding block. And we all agree that if I had a transaction that, brought my account balance below, below some certain value, and then I tried to make another withdrawal and it was going to overdraw my account, that we're going to reject that second transaction. And that's not an ethical or unethical choice. That's just an agreement that we say we won't honor transactions that are going to withdraw someone's account. But there's no basic ethics involved in these blockchain systems, right? There's some set of really rudimentary rules that that allow sort of what types of updates or transactions will be accepted by the system. And even this is governed by the people who are participating, right? If people decided to update their Bitcoin software to honor different types of transactions, then the Bitcoin system would allow that. But there's nothing in the system that says that this type of transaction is ethical or unethical. And so this is actually a real challenge, right? If people are pushing so if you're using these Bitcoin systems or cryptocurrencies or other blockchain systems to do things that inherently would be unethical, the blockchain itself isn't trying to stop you from doing that. And so you need sort of extra structures in place to handle that. And that's sort of a challenge. And that's one reason why we have some financial regulations and anti-money laundering laws, and the SEC is looking to regulate a lot of these cryptocurrencies specifically for this reason, that people are doing unethical things with them. Not just, you hear stories about people, purchasing illegal things, purchasing guns or drugs or whatever, but there's also a lot of essentially currency manipulation where it seems pretty clear that the some of the price swings in Bitcoin are through directed price manipulation by major shareholders. And those are the kind of things that the SEC tries to prevent, basically to make sure that the small players have an even foothold so people aren't sort of scamming you out of your money. And that's something that most of the cryptocurrencies weren't sort of designed for. And so now they're sort of struggling to figure out how to think about that. I don't know if that, again, if that's quite answers that question, but.
Yes, there is a lot of work to be done, it sounds like, in this field.
That's one of the reasons why it's a fun field.
Yeah, so go ahead and apply to our program, and then you can graduate and dive in, take an elective with Professor Hemenway here, or improve the world for the better with ethical hacking.
Yeah.
Great. Thank you so much for joining us today. Again, if you have a question that was not addressed in today's webinar, feel free to send us an email at online-learning@seas.upenn.edu. And feel free to check out our course on Coursera, Computational Thinking for Problem Solving, The early deadline for spring 2020 is coming up on August 1st. And then we also have a regular deadline on October 1st. So hope you can apply.